I'll bet I can teach you about an element of electric power that you don't know even exists, or if you do know, give you a new perspective on it. I'm sure you've heard of a watt, which is the basic measure of work in an electric circuit. It's your usage of watts that drives your electric meter and results in your monthly bill. But did you know that there are two other forms of electrical energy circulating in your wires? Called reactive current, or wattless power, or foam on beer, or any one of a number of colorful names, these two elements are circuit loads that heat up wires, use system capacity, and cause voltage problems. Although you don't notice them in your household circuits, they're there, all the time. The first of these loads comes from the requirement of some equipment to operate with magnetic fields, mainly motors and transformers. When an electrical current flows through a wire, two things happen to the wire. It heats up, you knew that, right? And the wire becomes a magnet, as this video clip shows. That's right, the wire becomes magnetic, and that's a good thing, mostly. Because that's why motors work, and it's what allows transformers to do their thing, which is to raise or lower voltage. Okay, quick review. What happens to a wire when current flows through it? Which choice do you think is correct? Remember, it warms up from the friction of moving charges, and it gets magnetic because the moving charge aligns magnetic forces already in the wire. Well, it takes energy to create that magnetic field around the wire. So when current starts to flow in a circuit, part of the energy that went into that circuit goes into creating the magnetic field instead of showing up as watts. Part of the energy is dispersed in the heat, too. If the circuit is DC, that's pretty much the end of the story for the magnetic field. But most circuits are not DC. They're AC, which means the voltage and current rise and fall periodically, 60 times a second in this neighborhood. If the voltage and current rise and fall, so does the magnetic field, since it comes from the movement of current. So now, 60 times a second, energy is taken from the circuit to make the field, and then added back in when the AC current changes direction and the field collapses. But it's not an even exchange. The energy is added back in all right, but it's added back in right at the time the current is trying to change direction, and it delays the change. You heard me. In an AC circuit, current and voltage change direction 60 times a second, but the addition of this magnetic reactive energy delays the change in current, actually throws voltage and current out of sync. The voltage and current sine waves are no longer rising and falling in step, and part of the energy applied to the circuit doesn't make watts. It makes the magnetic field, the reactive current, or volt-amps reactive, VARs as they're called. The more coils of wire there are in the system, the more demand there is for this magnetizing energy. So, during the day, when motors are running, air conditioners are fired up, and transformers are heavily loaded, VAR flow is high. Power system operators say the load is inductive because the moving magnetic fields are said to induce the opposing current flow in the lines. So the magnetic field causes a kind of load in AC circuits that operators call inductive, because the action of the magnetic field is said to induce current flow and make the change in current lag the change in voltage. So watts from straight resistance or heat is the kind of load we'd all heard about. The second kind is inductance from the moving magnetic fields as just explained. The third kind comes from another thing that happens when AC power changes direction. As you probably know, electrical energy comes in two flavors, positive and negative. Current flows when positives and negatives are separated, like when you scrape your feet across a carpet. John Travoltage shows us how here. You're physically separating the positive and negative charges, and when you touch something, like a doorknob, that has a different charge, current flows. In an AC circuit, the positive and negative sides of the circuit change 60 times a second because the generator that's separating the charges is rotating 60 times a second. So that means that each side of the circuit changes polarity when that happens. The side that has positive charges becomes negative, and the side that was negative becomes positive. Let's look at a simple example. Here's an electric circuit with a battery as the power source. Notice the open switch on the right side. Since the polarity of the battery doesn't change, it's DC, one side has a bunch of positive charges and the other side has a bunch of negative charges. With the switch open, they're just kind of sitting there, built up on either side of the gap. We know there's a kind of pressure built up between the points of that gap called voltage, that's right, and that if we close the switch, current would flow in the circuit from negative to positive. But now, think about this. What would happen if we flipped the battery around? What do you think? It's B. The charge runs the other way. Let's look at it. When the polarity switches, the battery forces all the negative charges to run around the circuit to the other side, and vice versa for the positives. It's like there's a reservoir of charges trying to keep that side of the circuit the way it was, while the battery is trying to change it. Of course, the battery eventually does, but in the same way that the effect of inductance causes a delay in the change of current flow, this effect causes a delay in the change in voltage. Substitute an AC voltage source, and this is happening 60 times a second. The effect is called capacitance, and equal amounts of it cancel out the effect of inductance. So capacitance causes a delay in the change of voltage in an AC circuit. Unfortunately, the system does not have equal amounts of inductance and capacitance. Since there are millions of coils of wire out there, every motor, every transformer, all acting like little reactive power generators, the system tends to be inductive, especially in the daytime, when factories are working and air conditioners are running. The effect of all those inductors is to overload lines and make the voltage drop because of the added resistance. The solution? Of course. If capacitance is added to the circuit near the source of inductance, the effect is canceled locally, and reactive power doesn't have to be transmitted through the lines, saving the capacity for watts. Each capacitor acts like a temporary battery, storing charge in part of the cycle and releasing it in another, causing a delay in the change of voltage. If planned and sized correctly, the delay in voltage change will match the delay in current change caused by the local inductance, and the circuit will have a minimum of reactive power flow. So that's my story, and I'm sticking to it. Aside from the watts used in your circuits, there are two other types of load: inductive from the magnetic fields and capacitive from the changing polarity in all AC circuits. These extra loads use capacity, heat up lines, and cause other problems. Your power supplier takes various steps to handle them, but they're a fact of life for your electrical system. Thanks for watching.